Okay. Bismillahirrahmanirrahim. Assalamualaikum and good evening to our lecturers, Dr. Jila, and also my fellow teammates. So we are from group 6. We're going to do the heat transfer application where our daily life application is PC cooling system, and for industries we take the biogas from sludge production. And here are our teammate Muhammad Shamim, Ainan Shahira, and me myself, Muhammad Hanif. Start. Okay, heat transfer is the movement of thermal energy because of the temperature difference. And there are three types of heat transfer, which is first one is conduction, which occur across the medium. Second is convection, where it's occur between the surface and also moving fluid when they are at different temperature. And thermal radiation happens because there is that heat transfer by radiation between two surfaces at different temperature without absence of an intervening medium. That's that. And here are our daily life application, which is the PC cooling system. That's that. And how it works. So heat transfers that are involved in this application is forced convection and conduction, where the PC is cooled by air that moving through the case, and also it contains different kind of air fans in order to pull the cool air and in and push the hot air out. It's like okay. So we focusing on the heatsink, which is connected to the heat producing component like the CPU or VGA card, where heatsink are used to disperse heat more quickly and also known as the passive cooling in cooling the system. And heatsink is usually made up of aluminum fins with a fan connected to the top or side of the metal fins. And we can see at the diagram on the right hand side that there's a fan directs the air into the heat sink, and its hot air in the sink will expand and exit the sink, where it's sent to the outside of the case through the case cooling system. You can see there's a convection happening there and also conduction when it's transferring heat from the CPU or the VGA card into the heat sink, and then there's forced convection where the fan blow the hot air from in the heatsink outside. And as a consequence, the temperature of the CPU or the VGA card does not rise beyond a certain level. That's that. That's all.
Thank you. Thank you, Hanif. I will now proceed with some technical details and calculation for the heatsink of the PC cooling system. So these are some situations of problem related to heat sinks. So we have a VGA card that is a heat producing component, and it is normally mounted within a sealed rectangular enclosure. The cooling process for this card is implemented by attaching an aluminium heat sink with a conductivity of 180 watt per meter Kelvin to it as discussed previously by Hanif, and the base of the heatsink is 42.6 degrees Celsius, and it has dimensions of W1 equal to W200 millimeter, whereby the 6 uniform fins are of thickness T 10 millimeter and pitch 18 millimeter. So each fin is having a length of 52 millimeter, and the base of the heatsink has a thickness of 10 millimeter. So if the cooling is implemented by air at a temperature of 17 degrees Celsius, flowing through the heatsink at a velocity of 3 meter per second, that is convected by a fan attached to the side. So determine the rate of the heat dissipation of the VGA card under this cooling condition. And these are the what we call that, the diagram, how including the heatsink, its dimensions, and the convection properties here. So the assumptions made for the calculation is we assume that the average convection coefficients associated with flow over thin surfaces may be approximated for a flat plate in parallel flow. And this is very important for us in determining the H value as well as the formula for Nusselt number. And all of the electric power is dissipated by the heat sink, meaning that there is no the heat is not dissipated to the surrounding. So critical transitional Reynolds number used for the calculation is 5 times 10 power 5, and the properties are kept constant throughout the entire process. So the first step will be to construct the thermal circuit of the system, and this is the diagram shown. And from the circuit, we can deduce the Q relations, which be Tb minus T infinity over Rb plus Rt and 0. And we can, so based on this formula, we know that Rb and Rto is the unknowns, and we need to find these two unknowns before proceeding with the calculation. So we can calculate Rb from the conduction, from the thermal circuit conduction formula, which is Lb over KHS W1 times W2. And but for to get Ro, we need to recall back to subtopic of heat transfer for standard surfaces under chapter 3, whereby we can get the overall efficiencies of fins from this formula, and then the effective resistance RTO is related to what to this relation. And so what we call it by simultaneously combining these two equations, we can get the formula for RTO, which is this one. And as you can see from this formula, there are a few unknowns that we need to determine, which is the H bar, as well as the A area of the fin and the total area of the what we call that of the conductions, and as well as the efficiency of fin. So to get so by referring to table 3.5 for straight rectangular fins, we can get the value of AT, LC, and efficiency of the fin, and M, and then these are the formula from the table. And then to get our convection coefficient, we need to have the Nusselt number. This is and we are going to assume that the convention is approximated with similar to the external flow of the flat plate. So to get the Nusselt number, we have to look for the Reynolds number first, and we obtain that the flow is laminar, since since the Reynolds number is lower than the critical Reynolds number used. And from table F4, we can get the properties of the air, and as well as at 290 Kelvin by linear interpolation. And the next one came from table 7.7, which is the what we call that the Nusselt number relations for flat plate. We can get for laminar flow, and with a Prandtl number of 0.6, we can use this formula to get the Nusselt number. And with this Nusselt number, we can further proceed with calculating the H bar value for the flow. And next one, we can solve RTO, but then we need to find the AT and efficiency of the fin first, using the previous formula that we have obtained from the table 3.5, and we get AT as 0.07 and AF as 0.011 meter squared, and the efficiency of fin is 0.177. Sorry for that. And next one, with the unknowns now. Now that we have known all the unknowns, we can already calculate for RTO, which is by substituting the values into the formula, and we get 0.0395 kilo per watt for the RTO, and then the RV is 5.56 kilowatt. And then now that we have we have TB and T infinity with these two values as well, resistance values, we can now get the heat dissipation rate by substituting it to the thermal circuit relation previously, and we get the heat dissipation rate of the heatsink is to be 648.02 watt. Okay, that is all from me. Thank you.
Hanif, we cannot hear you.
I'm sorry. So it exchanger is a device that enables heat to flow from one fluid, which is a liquid or gas, to another fluid without the two fluid mixing or coming into direct contact. You can see it in the diagram at the right hand side. That's that. And here are our industry's application, which is the biogas from sludge production. That's that. And how it works, the sludge heat exchanger is primarily used to heat municipal sludge or manure for aerobic and anaerobic digestion. And it's typically used in conjunction with a digester in the recirculation loop. And it usually works by using the heat sludge with hot water or to recover heat from hot outgoing digested sludge to heat the cold incoming sludge, and which it increasing biogas generation and helping in the manufacture of class A biosolid. You can see at the diagram at the right hand side that you can see the heat sludge also can be used back to heat the cold sludge that are entering the heat exchanger. Is that? And heating sludge is to harness energy by capturing the biogas. It's a green practice utilized to around the world in sustainable farming to capture methane gas. And the biogas that are produced can be used to generate power by using a generator, and this energy can be used to power the plant to power the other plant operations. And moving on to the next slide, just from Shamim.
Okay. So thank you, Hanif. So I will be handling the biogas from sludge production in terms of its technical details and calculation regarding its heat exchanger. So next. All right. So this is the question where a sewage treatment plant uses a counterflow concentric tube heat exchanger to heat up a sludge from 28 degrees Celsius to 50 degrees Celsius and hot saturated water in the annulus. So annulus is actually, for example, this is a donut-shaped object, right? So the area between the outer diameter and the inner diameter, this area is the annulus. So the annulus is where the water enters at 92 degrees Celsius and exit at 58 degrees Celsius. The thin wall in the tube has a diameter of 50 mm. Sorry, the overall heat transfer coefficient is 480 watt per meter squared Kelvin, and then the design condition calls for total heat transfer rate of 2.5 kilowatt, and we need to determine the length of the heat exchanger based on the parameters given. So next. So here are the information that gathered from the question, where we obtain the temperature of the inlet sludge, outlet sludge, and then the inlet water and outlet water. And next is the inner tube diameter and the overall heat transfer coefficient. And the last one is the total heat transfer rate. Next. So from those information, we can visualize some data where we can visualize how the heat exchanger looks like basically in a simple diagram. And then we can put in a simple graph regarding its temperature distribution, whereby the left side is the T1, where the sludge enters, and then the right side is T2, where the sludge exits. Next. So the governing equation regarding this question is the heat transfer rate, where we use the overall transfer rate times the surface area and times the log mean temperature difference. So here you can see the equation 1 generated. We required to obtain the log mean temperature difference to find the length. Next. So for the log mean temperature difference, first we need to find T1 and T2, where we just simply subtract the temperature of the water and the sludge at the T1 area and also for the T2 area. And then we use the equation to find the log mean temperature difference, and we obtain 34.53 degrees Celsius. Next. So then we insert the log mean temperature difference into equation 1, and therefore we got at about 96.02 centimeter. So I hope from this presentation there's something that we and you can learn. And thank you for your attention, and thank you, Doctor.